So I'm Abdulla Kafi. Currently, I'm a doctoral student at Kyushu Institute of Technology. So this year, this is my team. So we have team from like Japan, Mexico, and also me from Bangladesh. I'm originally from Bangladesh. So our proposal is a moon rover. So these are the teammate you can see here. And okay, so let me start with why we are doing this mission. So the main target is to find water on moon. So the objective is very like simple, easy, but has a very great impact. Why? So if we have if we can find water on moon, we can develop, like the in I sorry, things like if we have like water, we can make things on moon. So that's why we targeted very simple objective, but and our VISTA-PIPR, we call it VISTA-PIPR rover in short. So this will try to search water on moon. So we have divided our mission in 5 main objectives. The first one is to like search like the subsurface ice. So yeah, so our rover will go and try to see whether there is a sign of hydrogen or like oxygen to have the idea about the water. The next one is like to have an immersive VR model. So we have like we want to have a 360 view of our the terrain of the targeted area. So to make a virtual reality things. So we want to make a to fully digital things that can also replicate for the future missions. So the next one is to validate the extraction. So uh, searching water is I think it's not the only thing we can do. Like the next one is to how we will collect the things, like how we'll collect the water and how do the sampling and everything. So we need to validate those things also. So that's our like third target. So we develop something like extraction mechanism, and we want to prove that thing. And our target is to at least move our rover at least like 500 meter, so that we can like grab the area like and make the virtual reality. And the last one is the autonomy demonstration. So we have some onboard computer which will support some autonomy demonstration. So mostly related to the like obstacle detection and other things. So this is our rover at a glance. So we targeted the volume of this one is like 3530 by 30 centimeter, and it's a like 4-wheel drive. So we have individual control in each motor. And yeah, the targeted weight was like 10 kg, and we tried to compact everything within like 9.779 kg. And the main motherboard of our system is the Jetson Orin. And yeah, so we have a LiDAR system and also depth camera. So I'll show you in the next one. So our target is to implement the SLAM like algorithm for navigation on board. So this is the detailed view. So if you see, so this is like we tried to compact everything in a very small area. So we have an expandable like antenna and also the LiDAR system with the like 360 cameras. And if you see this part, like this is the rocker suspension. So we tried to make it in a different way. I'll show you in the next video, like next slide. So in the detail model. So here you can see, so we tried to make like install everything within our rover. So we have a wheel which can also scoop the like lunar soil, and we use some lithium-ion battery. Most of the component are like COTS component, like the Jetson or in these are like already available. Also the NIR system, the neutron spectrometer, and our main scientific payload was the neutron spectrometer and the near IR spectrometer. So with neutron spectrometer, we will try to search the like hydrogen elements, and after collecting the sample, we using the near infrared spectrometer, we will try to like prove the concept of whether there is like water elements or not by heating it. So how we reduce the weight of our system? So we didn't follow the traditional way of making it. So we tried to make the structure with a honeycomb structure, and we did an analysis with honeycomb structure and without honeycomb structure. So if we saw that in the simulation with honeycomb structure, if you put weight force from different sides, so it can at least have enough system to hold the weight in all side of the structure. So for the energy, we try to put the solar cell on each side based on the location where the rover will be landed. So we have a 30-watt peak system with EPS with maximum power point tracking. So this is also a cost product, and we calculated everything, and we saw that we need at least a 64-watt-hour battery system to run all the things and all the mission. And all the mission will not work together. So it's step by step. I'll show the concept of operation later on. So for the link, so we have UHF because the rover is small, and as you saw, we can't put enough power on board. So we try to focus on UHF. So the lander we will use with the lander, and the rover will communicate mostly with the UHF, and the lander will communicate to the earth through a X-band. And also, if you see, remember our rover. So in this side, we have also X-band. So if somehow lander fails to communicate with the ground, so we can at least send some beacon, the telemetry data from our rover directly to the ground with X-band. But the data rate will be very slow in this case. So this is our concept of operation. So after landing on the moon, we have a particular site where our moon will land. So after landing, so it will do the initial operation. The initial operation will be done using the 360 panorama view and also the LiDAR sweep, because we need to have the initial map of the surrounding. So we will create the baseline map first after it's deployed. Then it will just move a very small path, like 10 meter to 50 meter fast. And in each point, it will try to do the autonomy execution. Then we will try to do the panoramic imaging. So as we calculated, if you want to make 50 meter, 500 meter terrain, so we at least we need to have a 6-point imaging. So that will be the target. And with that, we can at least cover 50 meter radius digital twin of the lunar area. So in each point also, it will try to, with the neutron spectrometer, it will try to search whether we have some water elements or not. So if detection is established, then we will try to sample the things with our drilling machine. So if you see in the front of our rover, we have a drilling mechanism. So we have a video in the next one. So we will drill and collect the sample, and it will be heated inside, and we will use the neutron spectrometer to detect whether there is any vapor or not. And then the data transmission. So this is our targeted area. So we targeted the Shackleton Rim area mostly. So why is that? Because from the previous data from our literature review, we found that so in the polar region, so there is a possibility to have some water elements, because most of the time it has been like in the shadow area, and from like some others rover like and also the orbiter, so we have some idea that it has some hydrogen or some elements which can be related to the water, and that's why we choose this particular area. So our rover will land on the land close to that Shackleton ring and try to start the mission. So like with our rover, we are not only it's like a technical thing, so we are also like try to create impact societal. As right now, the like we don't have enough good data for from the South Pole region, so we will try to get those data if it's successfully like implemented the mission. So we will try to get those data, and it will help the other people in the future to know about more regarding the South Pole area. And in technical, so as like it is very if you see from here, like from Earth to Moon is very hard to communicate, and it has also a very latency. So we try to implement some autonomy system, so it will be based on meta reinforcement learning. So it will try to understand by itself on the spot. So this will help technically to the technical community, so for have like more robust autonomous system. And also if we can prove our like sensing and sampling mechanism, so that's also will help the future Artemis era, because in the future Artemis mission also targeted this region. And in the if you say from the education perspective, so like we will have a very good VR model of our system, and also we can build the digital twin of that particular area. So if you can give them to the like education institute, they will be like the future or next generation engineer will learn about those moon area very easily. So that's our target. So yeah, so we also have some risks. So if like the main autonomous like things is for we are using LiDAR. So if LiDAR fails, so if you see here, like we also have some stereo vision. So at least we can cope up with the things. And yes, if communication loss happens, so we try to make a like a beacon system which is direct to Earth. So from lander, like from the rover, we will try to send at least the beacon. The mission data will not possible, but the beacon, like whether the system is like working or not, we can at least understand those things. Yes, so if power like shortfall happen, like if we run out of battery, so our target is we try to fulfill the mission with within one lunar day, which is 14 days in Earth. So, so we have implemented inclined solar panel system. So if like power shortfall happen, so we try to find the sun area, and we try to recharge the battery with that thing. So that's the like thing we try to solve. And the sampler issue, so if like yeah, the mechanical sampling fail, so it's very risky. So that is one of the critical elements in our mission. So we try to do with like more like before launching it. So we try to test it more rigorously, so that yeah, and we try to make it very simple also. So yeah, so it will like be like we will have a full proven system before launching it. And for data loss, so we have a very like on JSON, we have some memory, and also we have a backup memory for the buffer system. So that's how we try to make the data loss much lesser. So the budget is explained here. So based on the like four categories, like hardware testing and the personal operation. So we didn't include the lander and the launch because yeah, we are trying to find like some like organization who will help with this thing. So after that, so this budget can be adjusted because that is totally unknown to us right now. And the like cost is little bit less if you see, because we are trying to make it everything within the student environment. So our project is totally focused on the like universities, laboratories. So that's why we try to make everything like with collaboration or with like multi lab collaboration. We try to decrease the weight. So if I show you the timeline, so our project is like 36 months long. So our target is we totally followed the system engineering approach. So we have like the first SRR, like system review. So first like 9 months, we will focus on the like requirement analysis, like prototype building and the CAD and thermal analysis. And in phase two, so we divided our whole program into like 5 phases. In phase two, our main target is the PDR. So before the PDR, we try to like prove our like VR digital twin prototype system, that one. And also the test, we have a test bed in our lab also. And also we are like looking forward to other lab to like do the testing for our initial prototype. So in phase three, our main target is the CDR, and before the CDR, and our targeted month is like 20th of month, like of from the starting. So we by that time, so we will try to do the all the subsystem integration, and also we will try to focus on the autonomy system of the software. And in phase 4, 5, so like yeah, so we'll try to do the thermal, like mostly the thermal vacuum testing and other facilities like full communication or full long distance test. So these are the target. And yeah, so by the end of this year, our target is like the FRR and LRR. So we made a like concept video, so how the thing will work. So from the lander, it will go to the near to the rim of the Shackleton crater, and then it will like start excavating. So this is our like drilling system. So it will like first expand, do the imaging, and it will drill. And here is the chamber where we will put the sample. And inside we have the NIR for like detecting the like water after heating it. So that's all from my part. Thank you very much, UNISEC-Global, for giving me this opportunity to present it here.